Okay, good morning. Week 13, Friday. We'll be focusing on centric buckling. Okay, for the last topic. I decided not to go into the last topic should be not the last topic. Actually, the topic I was going to cover is on displacement due to bending moment. And I've spoken to students that have taken this course. They're taking 3E now. They say they are having so much trouble with buckling. Okay, so I switched the topic and decided to do buckling. Okay, because they are struggling in 3E. Okay, and they are struggling of buckling because they have not a clue what buckling is. Okay, so that's why I'm focusing on buckling. Okay, right. So let's look at buckling. So the first thing about buckling is buckling only occurs when structures are under compressive or compression loading. Keyword over here is compression. Okay, and compression, I will highlight over here under compression axial loading. Be more specific. Now it can be both centric or eccentric. Okay, so for this class, I'm only able to cover centric. Okay, if we are going to go to eccentric, probably I need another hour or two. Okay, so let's now, before I go on, is how does mechanical properties how does mechanical properties relate to stiffness of a structure, right? So two words to focus on. One is mechanical property and how is stiffness affecting mechanical property. Okay, so let's focus on a structure under compression. Okay, let's look at a structure under compression. So if we have a built-in at one end, and then we have a structure over here, and the green line I'm going to sketch is our neutral axis. Sorry, centroid, not neutral axis. Our centroid. So this is so-called our centroid. And then we have an apply. We are going to apply a load later on. Okay. So let me finish sketching over here and doing some labels. So over here we have our length, L0. Okay. And we have our A, which is our cross-sectional area. So now if we put a load, if we apply a load P at one end, at the other end, at the free end. So now when we apply load P at the free end, so this is where we apply our load P, right? So what we realize that the length has been reduced. The length has been reduced. And this is now our L1. And we are aware that the distance from the original to L1 over here, this is our change in length. Okay. So as I say, we are on a topic of buckling. Why I do compression? Because buckling will only occur in compression. Okay. So once you do this, or when you are doing a test like this, the outcome you get, or the data that you get, is this. This is stress. Sorry, this is strain. This is stress. And what you will see, you see a graph drawn this way. Okay, where over here, this is your Young's modulus. Okay, there is your Young's modulus. Now, some of you will say, Eugene, why do you draw on the third quadrant, right? Why do you draw it? If you look at how the test has been carried out, okay, realistically, the stress is equal to minus P over A, right? It's on compression, right? And the strain is equal to L1, or L1 minus by L naught divided by L naught, right? What you will get is negative delta L over L naught. So in terms of stress, right, this is negative. In terms of strain, this is also what? Negative. Okay. That is why I draw in the third quadrant. Okay, but most of the time, okay, what we tend to do is we tend to ignore that. We tend to draw in the positive side. Okay. It reflects the same thing. Okay, we just get rid of the negative. Okay. So we know this line over here obeys Hooke's law. Okay. It obeys Hooke's law, where normal stress is equal to epsilon E multiplied by epsilon. And we are going to call this our equation number 1. Okay. And this equation where we have in terms of epsilon, this is our equation number 2. Okay. And then we know that normal stress, I've written this before, is equal to minus P over A, right? Because it's in compression. And then when we substitute equation 2 and 3, right, into equation number 1, so equation number 1 is minus P over A, and then this is equal to epsilon minus delta L over L naught. Okay. So what we get from here is we get the change in length is equal to P L naught over AE. Okay. So you have seen this formula before, yes, in P2P04 under axial loading, where probably, not probably, I'm very sure Dr. Koshi taught you about axial loading, and he taught your axial loading that is statically indeterminate, yes or no, right? And you also learned buckling, thrust analysis, right? So this is our equation number 4. Important thing to take note, okay? This is only true when the material is in the elastic region and material were not buckle. Okay, the material will not buckle. Okay, right. So this is how we relate mechanical properties, right, to deflection. How about stiffness, right? Remember the objective over here is how to link mechanical properties to stiffness. So now if we look at stiffness, and I believe you all have done some sort of mechanical vibration, probably in high school or in physics, okay? How many of you have done mechanical vibration course in mechanical engineering in McMaster? Probably some of you who are in management courses. Have you done mechanical vibration yet? No? Okay. Right. So how do we relate stiffness? Okay. So I'm going to sketch another graph now. And this is to relate y. So y down here equates to deflection. Okay. P over here relates to the applied force. And then if I draw a straight line, right, this is what we call K, small k. So small k is stiffness in Newton per meter. Okay. So we know P is equal to K multiplied by Y. Okay. So this is our equation number 5. Okay. And we want to take note that Y, which is our deflection, is equal to delta L in equation number 4. Okay. So now when we equate equation 4 and 5, right? We have P, right? So P, so when I say equate, right? We equate equation 4 and equation number 5, right? So delta L is, or Y is equal to P over K. And this is equal to P L naught over AE. Okay. We know that we can get rid of the P, right? So stiffness, K, is equal to AE over L naught. Okay. So this is equation 6. So when someone say that this material is stiffer than the other one, okay, it is not just a mechanical property. When I say it's not just a mechanical property, it's not just based on Young's modulus. It's a function of your area, cross-sectional area, and your what? L naught. Or your original length and your cross-sectional area. Okay. Unfortunately, in buckling, right, in buckling loading condition, where the L over A ratio is very high. Okay, means the length is so much bigger than the cross-sectional area. Okay. Equation 6 is not valid. Okay, it's not valid. Why is that? Why is it not valid? This is because the deformation, or why is it not valid? Okay, why is it not valid?